All right, we've made it to the end of chapter 2, and we will start section 2.7, related rates. So lots to say here, lots to say. We've reached a point in the class where we finally get to do something useful, work problems, all right? Some applications to the differentiation that we've done up to this point. This will be one of the most challenging sections in the class. Students struggle with this because it's word problems. When I first learned this, I was a bit intimidated, but I think the more of these you do, the more you might come to actually like this stuff. There is an expectation here, starting off, okay, that you will have to know some geometry, some trigonometry, some basic areas, or basic formulas for areas, volumes, and, triangles, similar triangles. There's a bunch of different stuff that could come at you here. So just be ready if you need to do some research on your own to try and find formulas if you don't know them offhand. All right. So there is a set of steps that I'm going to give you here. This isn't necessarily the same. Every problem is going to work out the same, but these are the basic 6 things that I think you should do to help you through these problems. When I talk about these steps right now, they're not going to make any sense at all until you see some problems worked out in class, but at least you can come back and reference this when you need to. So the first thing we want to do is draw a picture of the scenario that we're looking at for the exact moment in question. So we're going to be drawing a picture. And then the second one, we're going to draw another picture, but our picture is going to be slightly different than our first one because it's going to be what we'll call our general picture. And then our third thing is to assign variables, rates, and constants into our pictures. We want to write down everything we're given, and we actually want to write down what it is we're trying to find. Then the fourth step will be finding an equation that relates the variables together. Then we'll use implicit differentiation to differentiate that equation from number 4. And then we'll plug in constants to try and get an answer. So again, at this point, don't worry too much about what that all means. Once we get to an example, you'll see how this works. But more importantly, let's get to the idea here and what is related rates all about. So before I begin getting too deep into this, let's just say that we have a circle. All right, if we have a circle, I want to make sure you understand that these are the things that I expect you should be able to do coming into this class. All right, if somebody gives you the radius of the circle, then to ask what the area is, you need to know what the area of a circle formula is, and it's pi r squared. So you should be able to compute the area given the radius. If I give you the diameter of the circle, then you should also be able to get the area because you know that the diameter is twice the radius, so you should be able to do that. If the diameter is 1 foot, then what's its circumference? So here you need to know the formula for circumference. If the circumference of a circle is given as 100 inches, then what's its area? So somehow the area and the circumference are related to each other. Can you figure out that relationship? And then the last one, if I give you the area of a circle, can you find its circumference? So in all of these problems that I've just given you, I want you to notice that our circle was what I'm going to call static, or in a static state. It was just stationary. The circle was fixed. Nothing about it was changing. The radius of the circle was whatever it is, and that's all. So nothing was moving. All right. In this section, we're not really interested in things that are in a static state. We are going to be looking at things that are moving, changing with time, and then we're going to be trying to figure out the instantaneous rate of change of that. So more specifically, we want to know the way that the rate of change of one variable of an equation affects the rate of change of another variable. So again, we're not going to work through any of these problems right now. We're just going to try and get the geometric idea of these things down. We've got quite a few examples here for us to look at. So let's take a look at the illustration below. And I want us to notice a few things here. Let's see. Why is this still here? Give me just a second. try it. There it goes. All right, so we have an expanding circle. I think I'll make this larger. We have an expanding circle here. Right now I'm going to check, I have the play animation checked. So this is the animation rate in feet per second. So I'm going to just click play, and we're going to watch a circle grow here. And it's growing in a way that the radius is changing at a constant rate. So as you watch this radius, the radius will go from the center to the edge. That is just growing at a constant rate, whatever it is. It's actually 1/5 of a foot per second. If you want, you can change the rate that it's growing. Now it's going to be 1/2 a foot per second. Just go a little faster now. There we go. And then I can make it grow even faster if I want. And this will go real quick. All right. So notice on all of the problems that I've given you a rate at which the radius is increasing. But the rate that it's increasing is constant, whether it be 2 feet per second, 1 foot per second, 1/2 a foot per second, 1/5, or 6. I didn't do that. That's going to be just ridiculously fast. Go ahead. Go ahead. Fine. So in all the problems, we have a constant rate of change of radius. But how about the area? How is the area and the radius connected? So I'm going to go back to 1 foot per second here. And notice that I'm going to pause this. Let's go backwards to about when our radius was 1 foot. Our area was about 3.08. When I go out to about 2 foot radius, my area is now 12.96. So it's grown significantly, even though in the first foot it grew to about 3 point something. As I went out to the second foot for the radius, it grew by more than 3. It grew by almost, 9 or so? And then if I go out and I make my radius go another foot, look at that, it's jumped up to 27. So I have a little table, a way of summarizing all this. I'm going to uncheck the play animation box. And this right here is a little thing you can play with. And what we have is the step. I can change my radius. Like right now my radius is set at 4, right? If I want, I can set it to 3 or set it to 2 or 1. So I'm stepping my radius right now up in increments of 1. If I wanted to and make my step sizes 1/2, then I can start at 0. Now my radius is 1/2, 1, 3/2, 2, and I can step that way. Now this table, our list of numbers, tells you a couple of things. Let me go back to a cleaner one right here. This first number in all these lists right here is the actual radius. So if my radius is 0, the next number is the area. So the area of the circle would be 0. If my radius is 1, then the area of the circle is 3.14. This last number is how much it's changed since I stepped up 1. This is how much it's changed. So obviously it went from 0 area to 3.14. So the net change over that first foot of radius change is 3.14. Now if I step to the second foot, so 2 foot radius, now my area is 12.57. That's a change of 9.43. So from 0 radius to 1, the area changed by 3.14. From 1 to 2, the area changed by 9.43. As I go from 2 to 3, the area is going to change by 15.7. And as I keep stepping, the change in the area is getting larger and larger. So every single step for the radius corresponds or correlates to a larger increase on the area. So it's not just, okay, you double the radius, you double the area. You double the radius, you double the area. That's not what's happening here. As we increase that radius or double it, then what's happening is the area is going up, but it's not doubling. But there is some relationship here. That's what we're going to be trying to do. We're going to be trying to figure out how this area and how this radius are related to each other, and then try and figure out instantaneous rates of change. That would mean, going back to this, if I were to ask you right there, right there, freeze that moment in time. At that instant, how fast was the area changing? Area, the instantaneous rate of change of area. So right there, the instantaneous rate of change of area, that's the question. So hopefully you understand the picture first to start. So here's a problem, I'll do it in class. If the radius of a circle is increasing at a constant rate of 1/2 foot per second, how fast is the area increasing when the radius is 4 foot? So that would mean, let me make the radius increase at 1/2 foot per second. Okay, let it go. And I want to know how fast the area is increasing at exactly the moment the radius is 4. Right there, right about there. I went a little over, it's okay. But right about there, how fast was the area changing? All right, that'll be fun. Here's a different problem. Now, in this circle, what's going to be happening is I'm going to be looking at a problem where the area is increasing at a constant rate. In the previous problem, the radius was increasing at a constant rate. So what I'm going to do is I'm going to play this animation. Okay. So what's happening here is that I have it set so that as the circle grows, the area is changing at a constant rate. So it has to grow slower at the end. I mean, you'll notice the radius of the circle is getting slower and slower because every time it steps out, it adds more area to the circle. And what we need is that the change in area per unit time be constant throughout the problem. You can notice it from here. If you just look at the numbers here and just notice the way they're counting here. We'll wait till it go to the area numbers 2, 4, right? The way it's counting through the area numbers is constant. It's like a watch, you know, it's just counting through the numbers. Every number is coming at the same rate here. But notice what's happening with the radius. Okay, I'll wait for it to start over again. Look how quickly it goes. 1, 2, 3. Now it's slowing down. 4, 5. See, it's getting slower and slower. It's taking a long time to get to 6. 1, 2, 3. So what's happening is the area is growing at a constant rate. My radius is not growing at a constant rate. In the very beginning, it has to grow very quickly, but as I get further and further out, the rate at which the radius is changing is slowing down. So hopefully that makes sense. You can also go here and you can, let me bring up, you can get less things here. So here again, you can fix, like, these are areas now. So 0 area means you don't have a circle. If the area is 3 pi, that's your circle. 6 pi, 9 pi, 12 pi. So those are the different circles corresponding to those areas. Notice my areas keep going up by 3 pi, 3 pi, 3 pi, 3 pi, 3 pi, 3 pi. So when you look at this again, this is radius, this is area, and this is change. This would be our change. In this case, it's our change in our radius. So what's happening here is first, the area is going, we're looking at the first number, or the middle number here. The area is going from 0 to 9.42. So it goes up from 0 to 3 pi, that's this. And the radius changed from 0 to 1.7. So I have a change of 1.73. It did a little rounding over here, but that's my change. My radius changed by 1.73 when the area went from 0 to 9.42. Now as I go from 3 pi to 6 pi, that's 9.42 to 18.85. Now my radius changed by how much? Well, come over here, this number, 0.71. So every time my radius increases by, my area increases by 3 pi, my radius is growing, but it's growing slower and slower, because look at these numbers, 0, 1.73, 0.7, 0.5, 0.4, 0.4, 0.36, 0.33, 0.31. So these are getting smaller and smaller. So that corresponds to that picture we saw. In the beginning, the radius grew fast, and then towards the end, as you get further and further out, it gets slower and slower and slower. So what we're going to be asking in this question, let's see, if the area of the circle is increasing at a constant rate of 1/5 square feet per second, how fast is the radius increasing when the area is 5 5 square feet. When the area is 5 square feet. So we're going to be trying to figure out an instant in time again. We're going to be looking, we're going to say, hey, when the area is 5, I went past it. Oops. Let me back that up. I'm gonna back it up. Let me pause it a little bit. Take it back here. We want to know when the area is about 5, right about there, somewhere around there. When it was changing, right at that instant, if I froze it right now, I want to know how quickly the radius is increasing at that moment. So we'll do that in class. Close some of these up. All right. Next example, a sphere. So now we're going 3-dimensional. In this problem, we have a sphere with the radius increasing at a constant rate. So we've got our radius. Let me play this. The sphere is growing. How is the radius connected to the volume? If the radius is growing at a constant rate, how does it affect the change of the volume? So let me change it. Let me make it grow a little faster. All right. So again, you can turn this off. You can look at a table. When my radius goes from 0 to 1, the volume goes from 0 to 4.19. When the radius goes from 1 to 2, the volume goes from 4 to 33. So huge jump, a jump of 29, right? That's the change in our volume. If I jump another foot on the radius, then I increase to 113 for a volume. That's a jump of 79. So every foot that I go out in my radius, my volume is growing more and more. The rate at which it's growing is larger and larger. So let's see what question we have here. If the radius of the sphere is increasing at a constant rate of 2 feet per second, then how fast is the volume increasing when the volume is 36 pi? Wow. Okay, so let me see here. If I go back to the animation, we want to know how fast is the volume increasing when the volume is 36 pi. Well, what's the volume of a sphere? Well, you're going to need to know that, and you're going to need to somehow connect it to the radius and work this problem out. So in class, we will work through it. But remember, the main thing for now is to realize what we're trying to do is we're trying to let a sphere grow, and we're trying to say, okay, right at some point in time, how fast was the volume changing? Not what is the volume, how fast was it changing at that instant in time? All right, here's another one. This one's a little different because now instead of connecting the radius and the volume, I'm connecting the surface area and the volume. So somehow we have to connect the two together. How is surface area connected to the volume? And so it's the same basic picture. We'll work through that in class, but we'll see the difference between this problem and the previous one. I want to get to a couple of more examples. Expanding sphere. There's the problem that goes with it. Now, here we go with this totally different type of problem. A plane flying overhead. Let me get back to my initial settings. So a plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? So let me play this first. Here's our radar station. Here's our plane. So our plane's going overhead. It always has 2 miles. It's always 2 miles off the ground. The red hypotenuse of this triangle is the distance between the radar station and the plane. What we want to know is right at this instant, when the plane is 6 miles from the radar station, that would be, well, right about somewhere in here. Boom. Oh, I need to pause this. Snap to it. There it is. When the distance here is 6, how fast is the distance between them changing? Not how long is this. We already know that's 6. But this red line, how fast was it shrinking or growing at that instant in time? Because obviously that red line gets longer and shorter as the plane moves. So we want to know an instantaneous rate of change of that red line. Here's another problem, same thing with the plane, but now instead of looking at trying to figure out how fast the distance between them is changing, we want to figure out how fast the angle of the tracking radar station is changing. So instead, look at this angle right here. As the plane flies over at 2 miles high, that angle is changing. And at a certain instant in time, I want to know how fast that thing was changing. If you think about it as someone looking at it going overhead, how fast is their head turning at a certain instant? So I'm going to pause it. Let's look at the instant in time right there. Again, we want to know that instant in time when the plane was 6 miles from the radar station. How fast was the radar turning here, or the person's head, however you want to say it. But it's the instantaneous rate of change of the angle, as opposed to the previous problem where we wanted to know the instantaneous rate of change of the line between the two. That'll be fun. Okay, a street light. Street light is mounted on top of the 20-foot pole. Here's my 20-foot pole. A 6-foot man walks away from the pole at a speed of 7 feet per second. Maybe that's not walking, but okay, here's my man. How fast is his shadow moving along the ground relative to the pole when he is 12 feet from the pole? So here's my man. He's walking, right? He's walking away from the pole. What we need to do is we need to first show the construction of everything here. Where's his shadow, everything else like that. So I'm going to throw it all up here at one time. Boom. So, right, I'll freeze it about right here. Okay. So we've got from the light hitting the man, that's the shadow should be cast on the ground. This black part should be his shadow, right? The total distance from the tip of the shadow to the pole is the green. And what we're trying to do is figure out how fast is his shadow moving along the ground. So that means how fast is this point right here, this tip of his shadow, how fast is it moving along the ground? Look at it right there. How fast is it moving? Is it moving the same speed as the man? Or is it moving faster than him or slower than him? Or it depends on where he is? Well, we're going to answer all those questions, but we want to know exactly how fast the tip of that shadow is moving when he's 12 feet from the pole. So right here, when he is 12 feet from the pole, how fast is the tip of his shadow moving away from the pole? Conical cup. All right, let me get back to the beginning of this thing. All right, a conical cup is 4 inches tall, okay, 4 inches tall, 6 inches wide. Water is being poured into the cup, so imagine water is being poured into this thing at a constant rate of 2 pi cubic inches per second. How fast is the water level rising when the water is 1 inch from the top of the cup? All right, so let me start pumping water into this. So as I start to pump water into this, I want you to notice that in the beginning, the level of the water coming up, it was actually coming up pretty quick. I'm going to speed this up a little bit. It was coming up pretty fast. Notice in the beginning again, boom, it comes up real fast. But then towards the end, it starts to slow down. That's because we're pumping in the volume of the water at a constant rate. And in the beginning, there's less volume down here, so it fills it quickly. But as the cup spreads out, that volume of water has to fill up a larger volume, so it's going to go slower up the cup. We want to know, and I'm going to show the construction of this, we want to know, and I imagine cutting this cone in half and looking at it from the side. This blue triangle represents the height of the water. We want to know exactly how the rate at which this height is changing, right? It says how fast is the water level rising? How fast is this blue line here rising at exactly the moment the water is 1 inch from the top? Well, where's 1 inch from the top? Right there. When the height here is 3 inches, remember the cup was 4 inches tall. So when the height's 3 inches, that means there's an inch left. At exactly that moment, how fast was it coming up? All right, at exactly that. Here it comes. Right there. How fast was it coming up? The runner. All right. Let me fix this text here a little bit. Kind of got cut off. All right. A runner sprints around a circular track, which has a radius of 50 meters. She runs at a constant rate of 7 meters per second. Her friend is standing at a point 100 meters from the center of the track. How fast is the distance between the two changing when the two are exactly 120 meters apart? Okay, here's my track. Here's my runner. Here's our friend watching. Okay, so the runner's going around the track, right? At a constant rate of 7 meters per second. They're running, they're running, they're running. At exactly the moment that they are 120 meters apart from each other. And remember, it's a 50-meter radius track, so that's 50 meters. The friend's standing 100 meters from the center, so it's 100 meters from here to here. So that means there's 50 meters to here and then 50 meters to here. We want to know exactly the moment that they are 120 meters apart from each other, how fast the distance between them is changing. So that would actually be right here. That's 120 meters right there. But we want to know how quickly the distance between them is changing. So let me show you the construction of this. This we know is 100. This we know is 50. The green line between them is the distance between them. We want to know how fast that's changing, right? So let me play this again. That green side of that triangle is changing. And at a specific instant in time, right around there, right there at that instant, we want to know how quickly that green line was changing. Interesting problem. The ladder. Last one. A 20-foot ladder, here's my 20-foot ladder, slides down a wall such that the top of the ladder is moving downward at a constant rate of half a foot a second. So this ladder is going to start sliding, and the tip of the ladder is going to be coming down the wall at a constant rate of half a foot a second. At the moment the top of the ladder is 3 feet from the ground, how fast is the bottom of the ladder moving away from the wall? So here's my ladder, it's falling. Here's the tip of the ladder coming down the wall at a constant rate. Now this is kind of like slow-mo because, probably wouldn't fall that way. That's a little better. So this is coming down the wall at a constant rate. We want to know at a specific moment how fast this tip of the ladder is moving away from the wall. So let me snap to the instant in question. That would be right at that instant right there. How fast was this moving away from the base of the wall? So here's the construction. I have triangle again. You can see here, I want to know how fast this green side is changing at that instant that we snap to. We'll do all these problems in class. You'll get a better feel for it. I just wanted you to at least see all these problems beforehand so that when I talked about them in class, you have some idea of the geometry involved in these problems.